Hello to all of you. Good afternoon. It is really a great pleasure to have here Professor Vazirgiannis from École Polytechnique, the Institut Polytechnique de Paris. I've heard a talk by Professor Vazirgiannis a few years ago, at Forth actually. It was 4 years ago, Mihaly, and I was really impressed by all this research that he had done on graphs, on machine learning, and providing the software available. And we could see all these opportunities for collaborative research and making impact. And it is really a pleasure to have the opportunity to listen to his talk today. So his talk is going to be on machine learning for graphs, a very hot topic. And more specifically, he's going to talk on kernels and node embeddings. So, well, Professor Vazirgiannis he's an excellent researcher. He's a distinguished professor at the Department of Informatics at the École Polytechnique, Institut of Polytechnique de Paris in France. He has conducted research in several universities and institutes worldwide, in Fraunhofer, Max Planck, INRIA, in Greece, in the École Polytechnique Telecom Paris, in Tsinghua University in Shanghai, in China, in Deusto University in Spain. And his research interests are on deep and machine learning for graphs, for graph analysis, community detection, graph classification, clustering, embeddings, influence maximization, text mining, including graph of words, deep learning for word embeddings with applications to web advertising and marketing, event detection and summarization. And he has active cooperation with various industrial partners in the area of data analytics and machine learning for large-scale data repositories in different application domains. He has supervised already 28 completed PhD theses, and he has published 3 books and more than 100 papers in international journals and conferences. He has received several Best Paper Awards, and he has organized a lot of large-scale conferences in the area of data mining and machine learning. So it is a great opportunity to have him here with us today. So thank you very much for accepting our invitation to give a talk in the distinguished lecture series of the Department of Computer Science at the University of Crete. This talk is going to be in English and it's going to be recorded.
Thank you very much.
So thank you very much.
Maria, you can hear me well, right?
Yes, yes, very well. And you can do share screen.
Thanks a lot for your kind words. It is always a pleasure to be even virtually with you and your audience. So let me try to share screen. I believe you can see my screen, right?
Yes, we can. Thank you.
Okay, so it is always a pleasure to be in Crete among friends. I hope this can be physical at physical level at some point, like a few years ago, after this terrible pandemic. So thanks a lot again for the invitation, and I'm glad to offer this talk to your audience. University of Crete and Forth is well known for its excellence and contribution to education and sciences in Greece and internationally. So today I'm going to talk about the topic, an introduction topic to machine and deep learning for graphs as an introduction. So the outline is going to be that I'm going to give a very short and light introduction to the basic concepts so that we can all be at the same level in order to discuss then a little bit on graph kernels very briefly, and then I will touch upon the topic of node embeddings, which is the first stage of the two-stage process for graph embeddings. And I will put a little bit emphasis on an original, let's say, aspect of node embeddings, the structural equivalence-based embeddings, where nodes are embedded close in the embedding space, even though they are far away in the graph, based on topological similarities. So graphs are everywhere. Social networks or the internet itself is a graph, or even communication networks or power networks are modeled as graphs. We have chemistry, where chemical compounds are modeled as three-dimensional graphs with different labels on the nodes and different bonds among them. As we said, communication and massive transport networks can be represented as such. Even documents like we see here, for instance, we have this document and we can transform it using the graph of word approach into a graph, which is the graph of words of document D. And we can use then this graph in order to do text mining tasks. So what is a graph? A graph is a set of nodes that are connected with edges. Not all of them, but some of them. So the graph is characterized by the set of vertices and the set of edges that are essentially the pairs of nodes that are connected with edges. Apparently, these are sets, okay? And then we are interested in the neighborhood of a node. For instance, the neighborhood of node 1 is the set of nodes that are connected with edges. So it is 2, 3, 4. The neighborhood of 5 is only 3 because it is connected to only 1. And then an important concept is the concept of walk. So a walk is a sequence of vertices that are connected by edges along the graph, where we can have repetitions. For instance, we can go from 1 to 2, then to 4, then back to 1, and then to 3. So this is called a walk, and basically we don't like this cycle repetition. This is why we come to the concept of a path, where a path is a walk where there are no repetitions. Okay. Then we have the concept of a cycle. For instance, the path 1 to 4, and that ends at 1. So this means that it is a path where the first and the last node are the same. Then we have the concept of a subtree, which is an acyclic, no cycles subgraph, where there is a path between every pair of vertices. For instance, we have graph G. Between every pair of vertices, so for instance, between 4 and 5, there is a path. Okay, between 3 and 2, there is also a path. So between every pair of nodes, there is a path, there are no cycles. So this is called a tree or a subtree. And then we can add more information on the graph. For instance, we can add labels on the nodes. So these labels are a set. So for instance, in this example here, the label set is alpha, beta, and gamma. The idea is that the label of node identified by 1 is alpha, whereas the label identified by 4 is gamma. Apparently, the labels appear multiple times in the graph, and they can be used for supervised learning or classification purposes. We can also assume that we have what we call an attributed graph, where on a node we can assume that there is a vector of values that characterize exactly this node, and so each node contains or is assigned a vector that we can use in the computations when we do machine learning, and there are many cases like that in real life. Now, because we are talking about what machine learning is for graphs, so what is machine learning for graphs? We have the concept of machine learning from the traditional data. In this case, we have the concept of node classification, where given a set of nodes with known class or label, we are trying to build a classifier, learn a function that for a node of unknown classification, it can predict its label. So, for instance, it could be at the level of a social network to predict if a social network node is a human or a bot. If the human is, I don't know, in Europe, is a European or an Asian, etc. Then we have the concept of graph clustering, where the idea is that this is an unsupervised mostly task, where the concept is that having a graph, so for instance, if we assume this is a graph, we are aiming at discovering dense areas in the graph that are dense inside and loosely connected across. This is the known problem of clustering, but transferred to the area of graphs. Then there is a concept of link prediction, where we are trying to make predictions if two nodes in a graph will be linked in the future. For instance, will author A cite author B in the future? Will John be connected to Mary in a social network in the near future? And last but not least, we have the most interesting and demanding task, which is called graph classification, where given a set of graphs with known labeling or classification, we aim to learn a function that will map an unknown graph to one of these labels. For instance, the concept of graph classification can be illustrated with this slide. So for instance, we have the class -1 and the class 1 graphs. We see that the topological, let's say, feature that makes them different is that the class -1 is about open chains of nodes, whereas class 1 is about let's say, graphs that are a closed chain. It is a circle among nodes. For this reason, for these unknown graphs, G1 and G2, for instance, G1 will be, because of this topological similarity, mapped to class 1, whereas G2 will be mapped to class -1. Okay, so this is the kind of approach that we use, and the objective, as we see here, is to learn to estimate a function that, given an input, given an unknown set graph, is able to predict its label from the function that we have learned via this training set. Okay, it's a supervised learning description. Then we have the concept of graph comparison or graph similarity. Why do we care about this problem? We all know that doing machine learning is about identifying the similarity of an unknown classification graph to the prototype of the class. So similarity between graphs is essential, and it is a difficult topic. So the idea is that we would like to have a function S that takes as input two graphs and quantifies or results in the similarity between graphs G1 and G2. So if we have such functions, we can enable clustering and classification and in general machine learning issues. But the graph similarity is not an easy issue. I mean, there is the extreme case of similarity, which is the problem of isomorphism. Probably we all have heard about the problem of graph isomorphism, which is exactly the fact that we have a graph and another graph. And there is a mapping between the nodes of graph G1 and G2. So for instance, I can map 1 to A, 2 to B. And if there is an edge between 1 and 2 in the original graph, in the left, in graph G1, there has to be an edge in the next graph. And this has to be done for every node and every edge. If all nodes of the first graph and all the edges of the first graph can be mapped to nodes and edges of the second graph, and there is no edges or nodes missing on either sides, then we say that the two graphs are isomorphic. So in your opinion, graphs G1 and G2, are they isomorphic in this case? Who can tell us? Just to maintain some level of interaction in this virtual community that we have today. Well, apparently the two graphs are isomorphic, right? Because, let me change the color. We have mappings of the nodes to edges. So let's say the edge 1, 3 can be mapped to the edge A, D, and apparently node 3 has to be mapped to node D. So in this case, and of course, this is, but the problem of graph isomorphism is very strict. So there is one, thanks to Emmanuel Siligardos, that answered my question correctly. So the idea is that the problem of graph isomorphism is very tough, and we don't even know if it can be solved in polynomial time. It has been declared as the disease of algorithms, but still, I mean, if we add, for instance, this edge to this graph, the G1 and G2, they are definitely not isomorphic, but we still think they are similar, right? So in that case, we are interested in algorithms that are capable of measuring similarity between two graphs in polynomial time. And this is necessary because computational complexity is always a central issue when we do machine learning. So in order to do that, one way out is to map graphs into vectors. So if this is G1, this can be the vector that corresponds to G1. So by doing this vectorization or this embedding effort, we convert the graphs into vectors, and then we can compare the vectors of graphs, as we know, with inner product or other types of similarity. And this is what we know how to do very well in machine learning. In order to do that, then we adopt or we capitalize on the concept of a kernel. I believe many of you should remember what is a kernel. So what is a kernel? Essentially, it is a mapping. Let me see if we have, no, we don't. So what we have here is that, for instance, we have a graph here, okay? And we would like to map these graphs into a vector space where, for instance, G1 becomes f of G1, which is a vector, and G2 becomes f of G2 via this unknown mapping for the moment. And then we know that it's easy to compute the similarity by doing the inner product of fg1 fg2, okay, which is a vector now, okay. So this inner product computes similarity, and the challenge in the kernel domain is to find a function that takes as input the original graphs in the original domain without any, and computes a value that is identical to the inner product in the embedding Hilbert space. I forgot to mention that there are some properties that we need to make sure that this is a Hilbert space where inner product is valid and can be computed. So this is the concept of the kernel. It is finding a function that takes as input two graphs that computes essentially the inner product between the supposedly mapped graphs into the embedding domain, and informally this kernel between x and y is a measure of similarity. So let me start with the concept of graph kernels, assuming this. So kernels, as we mentioned, are functions that take as input graphs and give us back their similarity, and this similarity can be used in order to do machine learning. This enables a lot of applications, like in bioinformatics, in chemoinformatics, in computer vision, even cybersecurity, in NLP. We also have contributions there, social networks, etc., etc. Wherever we have information represented as graphs, we need to be able to do graph comparison via graph kernels. For instance, in the concept of, in the case of protein-protein function prediction, we have protein interaction data from which, with sequencing, etc., we can build a graph structure that represents these protein data, and then we can, based on this structure, we can do predictions of the functionality of an unknown, let's say, protein data. So this is graph classification, and we see that depending on the method, they can achieve an impressive accuracy for the prediction of the functionality. I am seeing some questions. Maria, do I answer now or answer later?
I think you can answer it later.
Okay.
I mean, I think actually the first one has been already answered, but let's keep the discussion perhaps towards the end.
Okay, I will
just to have a better flow of your talk.
Exactly. Okay. And then we have what we call chemical compound classification, where we have a chemical compound where the nodes are characterized by labels that have to do with the elements and the atoms. Then we have as well different types of edges, single or double bonds. And this creates a graph that is labeled both at the node and at the edge level. And again, there can be, for unknown functionality compounds, there can be very good classification predictions. And in this way, we can create new, let's say, chemical compounds with good prediction of how they behave. There is also the possibility of doing malware detection. So if you have a virus, the call functions, the function calls within the virus software seem to create a graph that is characteristic. So using graph classification, we can predict malware with an impressive accuracy based on only this topological information. There is also an interesting approach that is called graph of words that maps documents into graphs. As I mentioned before, this is work that has originated from our group in CIKM 2013, and my student Rousseau, with whom we worked on that, he's now an engineer in Google. So the idea is that a document creates a graph, but then from this graph, following a different path, we can create an abundance of different documents on the same vocabulary, but with different sequences. So so it can be seen as a document generator. Now we discussed about similarity between graphs, right? So it's like we have two cars and we are trying to identify their similarity. It's like two cars are similar if they have the same length, if they have the same color, if they have the same capacity engine of the engine, if they have the same, I don't know, other features. So in this manner, which is similar to the example I mentioned, we can consider similarity between two graphs if they have similar walks, if they have similar shortest path. Anyway, these kind of features are all candidates to use for computing the similarity between graphs, and they are all in the concept of what we call R-convolution framework. Since we have only 40 minutes, I chose to present only one kernel, which is probably the most important one, that is based on the so-called Weisfeiler-Lehmann test. What is this? It is a test that by renaming by renaming the nodes, it can answer if two graphs are not isomorphic at some point. For instance, these two graphs are apparently not isomorphic, right? Because it is apparent why it is not isomorphic, but let's see how this algorithm would find this out. So what we do is that we copy the labels of the neighbors of a node. So for instance, here in this case, the labels of this node are 1 and 1. The labels of this node are 1, 1, 1, 1, etc., etc. So we build this kind of message passing, as we will see later, mechanism that renames the labels of the nodes in both graphs. And then we have a renaming scheme. So this one became a 2, this one became a 3, etc. So we have new labels on the graphs based on this protocol that I mentioned before. And we have the two sets, for instance, for this graph, the set of labels is 2, 3, and 4. And for this graph, it is again 2, 3, and 4. Okay, so this means that this identity of the two sets of labels enables us to go a step further, having the chance that the two graphs are isomorphic. We do the same. So for instance, we do 2, 3, 4, and then 4 is a neighbor with 2, 3, 2 and 3. And doing that, we are enabling a second round of information passing that creates a new labeling scheme. And in this case, definitely the two sets of labels across the two graphs are not the same, because, for instance, 9 doesn't exist here. 9 doesn't exist in the left graph. 7, for instance, doesn't exist on the right graph. So these two graphs are definitely not isomorphic. Okay, so when the two sets of labels of the two graphs become not identical, then we can decide that the two graphs are not isomorphic. But until then, we had the chance to compute similarity between graphs as there was a chance that they are similar. So, as we said, graphs are not isomorphic. And then the Vazirgiannis framework, it enables computation of the similarity between graphs, assuming the similarity between the graphs, the original graphs, K is a similarity function, plus the same similarity function between the same graphs but transformed under the Vazirgiannis, let's say, transformation, which means label aggregation, etc., until we reach the point where the two sets of labels are not the same. So these are important papers of like 10 years ago. So for instance, let's see the computation of similarity between graphs G1 and G2. So these are the labels. We do, for instance, there is this framework that tells us what is the distribution of labels across the graph. So this is label 1, this is 2, this is 3, this is 4, this is 5. So there is one label 1 in the first graph, 2 labels 2 in the first graph, etc., etc. So the labels on the first graph are represented by this vector. The labels on the second graph are represented by this vector, and it is evident that we can compute the similarity by doing an inner product, that is in this case 7. Then what we do is that we do the label augmentation by adding to the labels of the neighbors, and we do the labeling renaming scheme. And as we see, apparently there are differences because 11 doesn't exist on the right-hand side and 12 doesn't exist on the left-hand side. So these graphs are definitely not isomorphic. So what we do is that we have to stop there, but we can still compute the similarity between the vectors corresponding to the labels, for instance, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the vector of the first graph in this case, the second graph. So the similarity between these two vectors is 3, and the overall similarity is the similarity that we computed before plus the similarity that we computed now, summing up to 10. Okay, so this is the result of the Vazirgiannis similarity framework for this simple kernel. As we mentioned, there are different ways to compute similarity with graph kernels. There are about 20 graph kernels, and we have in our group worked a lot on this topic, and we created a Python library that is implementing all the known kernels until 2020-21 that we were doing this work. And it is compatible with scikit-learn. It is open source, so therefore it can be extended, and it is available on this GitHub folder. Now, in parallel to that, we have conducted a large-scale survey, and there is this taxonomy of the different kernels, for instance, GraphNet, Lovas, SVM, etc., etc. So these are all the different kernels, and they are grouped according to different criteria. For instance, if they are using R convolution, or if they are doing explicit computation, or if they are assignment kernels, etc., etc. All this you can find on this large-scale survey on kernels that we published. And as time goes by, I am passing to the third part of the talk, which is based on deep learning. So far, we have been working with similarity metrics that are inspired by heuristics, named for different kernels. And this enables machine learning having the kernel matrix. Now, we have the concept of node embeddings, which is embedding nodes in a low-dimensional space based on an unsupervised process that is implemented with deep learning. So we have what we call representation learning for graphs. Representation learning means that we have a node of a graph and we map this node into a vector. Okay, so different nodes are mapped into different vectors, and so we are working on the node embedding layer. So this can be done by unsupervised methods like deep walk and node-to-vec that we will see briefly today. We can have supervised node embeddings where we have already known labels. There is the concept also of graph autoencoders where the input is a set of graphs and there is an intermediate representation being learned to produce. So this is the encoder, this is the decoder. It produces a new graph and the system is trained on the distance, on the difference, on the error between x and x prime. Okay. So, and then there is the concept of graph embeddings where we are embedding entire graphs as opposed to single nodes. But then we have the concept of node embeddings. For instance, we have graph G, and we would like to embed, for instance, this node. In principle, this is the adjacency matrix. And this adjacency matrix tells me that node 1 is connected to node 2 and to no other node. Okay? So what are the problems with this representation? The problems with this representation is that, so this is the representation of this node. The problems of this adjacency matrix is that it is very sparse, usually because in real graphs, we are far away from having a click. And it is of high dimensionality because, for instance, if this is 10 to the 6 nodes graph, then this will be also of the same dimensionality, and having sparse vector of such big dimensionality is only problematic, as we know from machine learning. For this reason, we are aiming at mapping the nodes of the graph into a vector space where proximity or grouping, for instance, in clusters in this case, is maintained in the embedding space. So for instance, the purple nodes are grouped together in the embedding space and so on and so forth. The important thing is that the dimensionality has to be lower, much lower. And this enables density as well. Now, the early methods included the so-called Laplacian eigenmaps, where the objective was that given two nodes I and j that are connected, for instance, and this aij is the weight or the existence of the edge or not, we are aiming at learning embeddings for I and j such that we minimize this optimization function. So what we are trying to do is that if the two nodes are connected, which means they have a high value for aij, then the embeddings have to be very close to each other so that they maintain the product and the sum of the products low. Otherwise, if there is no edge, this means that yi and yj, they can be arbitrarily far away to, and anyway, this is zero. So, so the idea is that there are embeddings produced in this manner. So the solution to this, because you see it is formulated like that, we are searching for the y, for the vector y that minimizes this computation, and apparently y is nothing but the top k eigenvectors and eigenvalues of the Laplacian matrix, okay, which is L. These are, of course, a bit old methods, but still good as baselines. So the idea is that there are different methods based on random walks, on edge modeling methods, on matrix factorization, etc. Let's see some of them. But before we move to these, let's say, concepts, it is important that we identify the different types of similarity, right? So what is the similarity? There is, for instance, vertices 6 and 7, they have a first order proximity because they are connected by a strong link, a strong edge, right, with a high weight. We have also vertices 5 and 6 that have a second order proximity because you see they are not connected themselves, but they know the same neighbors exactly. So their similarity is via the intersection of the set of the neighbors. And we can extend this even further. For instance, higher order proximities, for instance, A1 and A2 in this case, they have a lot of three paths between them, and so on and so forth, okay? So these are the different kinds of proximities or similarities in a graph. And then the first method that was ever let's say, invented and still very important as a baseline is the so-called deep walk that essentially transforms the node embedding problem inspired by the NLP, let's say, similar problems like word embeddings, where we convert the graph into a set of sequences, a set of documents based on the random walk. So for instance, this is V5, and then we can jump randomly to V8, and then to V32, etc. So it means that I do random walks following edges on the graph of fixed size. In this case, the size is 2, 4, 6, 7. So I have the graph, and this is the random walk transformation of the graph, and I can use these so-called documents and pass them to the skip-gram architecture that is well known from NLP. So we embed a node based on its context. So this is a walk 43151. We give as input to the architecture. Here is the architecture. Where is the architecture? So the idea is that we give these contexts, we give the middle node as input. So if we have this deep learning architecture, we give one as input, and we are trying to predict the surrounding nodes 4, 3, 5, 1 via softmax operation in the output. And this learns embedding because here, for instance, the dimensionality is D, and here it is the size of the graph. And so we have a mapping of nodes into a dimensional into a dimensionality D via the skip-gram architecture that is very well known. I will skip the it is basically maximizing likelihood and cross entropy. And then the problem with deep walk was that deep walk has a rigid search strategy, which means that it follows edges without any pattern. I mean, it follows randomly edges. But the node to vec is basically doing the same, but it does biased random walks based on the network roles of nodes. What are the network roles? This is the important thing here. So there are two concepts. There is the so-called BFS search, where I go from U to my immediate neighbors and come back, and this means that I learn my neighborhood. Or I can choose to start from, I can choose to start from U and start going away. So I am learning, or I'm visiting faraway areas of the graph. So in this case, U and S6, they have a similarity that is called structural similarity, heterophily as we call it, because they have the same or very similar structures around them. So even though they are far away, they play the same structural role. So Node2Vec interplays between these two extreme strategies, the local visits and the remote visits, DFS. And I am skipping some of the details, technical details that are not very important for the moment. And in this case, we have already seen deep walk and Node2Vec, and also there are other methods that can be, we have also seen Laplacian eigenmaps. And let's see how do we evaluate such methods. So basically there are some data sets, for instance, these data sets that are social networks, citation networks, and another language network with connections between items. And we have 3 tasks like node classification, link prediction, and visualization. These are the statistics of those graphs. So we have anything between 1,700 nodes and more than 1 million. And for edges, we have anything between 28,000 edges and 1 million, or this is even more than 1 million because it is fully connected. So the node classification task has to do with, for instance, the percentage of the data that we use for training, and we measure via using the different prediction methods, the F1 metric, which is the harmonic mean between prediction and recall, if you remember. And we see that SDNE is the best one in both cases. Laplacian eigenmaps is a bit problematic in this case. But in the other data sets that we have here, Flickr and YouTube, the node classification task, SDNE is always the best method, but the simple and good old Laplacian eigenmaps gets the second place in some cases. Also, there is the concept of link prediction, which is, I have a set of citations, for instance, I remove some of them and I train a model and try to predict which citations were removed. And we did this with an archived data set. No, we didn't do that. It was done by the paper that compares these methods several years ago. So this is the ratio of the removed links. This means that they have removed 40% of the edges, and still they could, with mean average precision of 0.3, predict well the missing edges. SDNE is always the best, followed by line, deep walk, and Laplacian eigenmaps. And also for visualization purposes, these are the embeddings of documents that are connected somehow in a graph with relevance edges, humanly edited. And we see, for instance, that after some epochs of training, the algorithms SDNE, line, and GRAREP, they separate nicely the 3 categories of the documents, right? Whereas deep walk doesn't manage to do, because they map the documents into mixed groups. And then there is the concept of structural identity. I mean, we have several dense slides, but I will try to introduce the concept of structural identity. For instance, we have different colors here. We have the red and the green nodes, for instance, the red and the green. And the slide says that they are structurally identical. This means that they have a structure that is identical around them. So they have this papillon around them. So for this reason, they are structurally identical. They are surrounded by the same structure. Therefore, they play the same role in the network. The purple and the brown, for instance, these two guys, the purple and the brown, they are having similar structures. Therefore, they are similar but not identical. And this is the baseline or the key idea behind the algorithm struct2vec, that is doing node embeddings based on the structural identity of nodes. I think we don't have the time to explain. It is a relatively recent paper in KDD by some Brazilian group. So the idea is that we learn structural identities of nodes at different levels, depending on the distance between the node and its neighborhood. So this is the neighbors at distance 1. This is the degree of the node. This is, for instance, this says that the neighborhood of node U has nodes that have degree 1, 3, 4, and 4. So this is the distribution of degrees of neighbors of the neighborhood at distance 1, 2, etc. So in this way, we build knowledge of the structure of the graph at different distances from the nodes, and there is this structural graph where we have the layer 0 similarity, the layer 1 similarity, the layer 4 similarity, and the structural embeddings are built by doing random walks between in and across such layers. So for instance, we can start from this one, I can go to this one, I can go to this one, and then I can jump at this layer, I can continue be doing that, and then with some probability I jump to this one. So what do we achieve by that? We create random walks that learn both local but also remote global structures. And then by having these longer random walks, we are able to do experiments with these very interesting artificial but very interesting networks, like the barbell graph, where, for instance, we see that the color denotes the structural role of the node. For instance, this node and that node, 1 and 2, they are far away, but they are similar because they have the same connectivity across. This one, 3 and 4, they are also very similar because they serve as the entry to this click, etc., etc. So even they are far away, they play the same structural role. And we see that DeepWalk and Node2vec, they fail totally on grouping these nodes, whereas struct2vec, the algorithm that I just, they manage to group together similar roles in close positions. Then there is another approach that is coming from our group, which is called structural node embeddings using graph kernel. Let me briefly, let's say, describe this. So this is about that we have a graph and we are creating 1 and 2 hop and 3 hop neighborhoods. For instance, from the green node, we create the 1, 2, and 3 hop neighborhoods. And then we give names, we give labels to the nodes representing their distance to the central node, okay? Then what we do is that compares the two nodes by computing the similarity between the different level graphs. So this means that if this is a green node, and if there was another node that was giving another 1, 2, 3 layer graphs, we would compute the similarity between this and that, between this and that, and between this and that, and we would multiply these similarities in order to get the global similarity based on the local and more global similarities with regards to the distance. So this is exactly what we mean by this kernel. And here is an example. So for instance, we have two nodes, the red and the green. And we have the first level neighborhood. KG is any kernel, any of the 20 kernels that I mentioned in the previous part, plus, and then we add the multiplication of the previous similarity to the similarity of the, let's say, of the two graphs created by, this is distance 1, this is distance 2, okay? So in this way, we create some similarity metrics, and then what we do is that we take this similarity matrix, we do the decomposition in eigenvectors and eigenvalues, and the vector, the ith row of Q, this is well-known, let's say, decomposition. The ith row of Q corresponds to the embedding of the ith node. And apparently, the dimensionality of Q has to be lower in order to achieve dense embeddings. And then we do different experiments introducing different types of structures. For instance, we introduce this house or star or fan in different cases, for instance, either identical or perturbed, which means that we have additional edges. And we see that the performance of the method that we introduce is always better than the competitive baselines in terms of both accuracy and F1 score in recognizing and classifying those structures. And then we have other data sets that comprise of all the three structures in the same graph, either clean or perturbed or labeled as well. In all cases, we see that our approach outperforms the rest in the graph classification task. And in the Endron dataset, which is a real-world dataset, we have a dataset with few nodes and edges, and we are trying to predict one of the 7 functions that the node has there. And again, as regards the performance on classification, this method does better results. There are other criteria like homogeneity, completeness, etc., in which we don't perform very well, but for the supervised learning task, we do very well. So that was a very short and fast introduction to graph machine learning. So what we do is that we propose methods of mapping graphs into vectors, either with graph kernels or with deep learning via node embeddings and such. And we use these embeddings in order to do the different machine learning tasks like node classification, link prediction, or graph classification. I hope it was, let's say, useful to report to you these things. If you have any questions, I'll be glad to answer them in the next few minutes.
Great. Thank you very much for your time. It was an excellent presentation and very informative. So thank you very much. So we do have a few minutes, like 5 minutes maybe.
Yes.
For questions.
Yes.
I know that we are running out of time, but so yeah, please, you can open the microphone. Maybe I have a very quick question to you until the other people can raise their hands or just speak up. So one question is the following: when you have different features, different ways to estimate the connectivity, so to build the graph, the original graph. So let's say that you have different features based on which you can develop the graph. What would be the best method to try to perhaps, ideally automatically, select the most prominent, the most appropriate features? I mean, is there any method to do this? It seems like a kind of like related to perhaps principal component analysis or dimensionality reduction in general. But I was wondering if this is a task that you do that as part of your methodology.
Well, actually, this is done somehow in an unsupervised manner because the node embedding methodologies, what they do is that they create embeddings for the nodes. Mm-hmm. They are converted into vectors, and then by doing some, let's say, clustering on those vectors, you identify groups of nodes that are close to each other and therefore more similar, and therefore you identify the optimal groups that and the common features of those groups are probably the optimal features that you are interested in to characterize this group, I think. I don't know if it answers somehow your question.
Mm-hmm. Okay, all right, I'll think of it a little bit more. Okay, great. Yannis Samardinos has also a question regarding F1. He has texted that in the chat of
Yanni, καλησπέρα. Thanks for being here.
Σε ξαναβλέπω στα μέρη μας διαδικτυακά εστόλα.
Έτσι. Ευχαριστώ πολύ για την πρόσκληση. So the idea is why F1 is preferred over the AUC. So F1 is the harmonic mean between precision and recall. So it is, let's say, a global metric, but also that refers to specific values of precision and recall. For instance, precision 50%, at recall 30%. AUC is more global in the sense that it covers all the behavior in all settings of precision and recall. You are right, Yanni, it could have been used, but it requires endless more experiments that are sometimes expensive to end. In this area, accuracy and F1 have kind of dominated.
Actually, what about I noticed that you are using the micro F1 and the macro F1.
Both are feasible. It depends if you are interested in the intra or in the interclass situation. These are well-known, let's say, differences for different machine learning methods. But the idea is that always combination of precision and recall is always more informative than using separately both of them. And we also know that accuracy in the case of imbalanced classes is kind of enabling not cheating, but when two classes are not balanced, then high accuracy doesn't really mean that we have a very good performance. We need the F1 score.
Exactly. And this is another comment question that Thomas is writing.
Yes, it's exactly. Thomas Dongas got the point. This is why I think AUC, as Yannis mentioned, or F1 score are safer metrics to report if we want to have really the the most informative performance of our method.
Okay, great. So thank you very much for your time. I don't want to take more of your time. So it was a great presentation, and we'll review your papers. We'll go and check also your software. And thank you very much for making it available.
Thank you very much, and it was nice to have all of you there. I see a great audience. So thanks a lot. And if you have any further questions, please contact us. We'll be happy to answer.
Great. Thank you. Thank you. Bye.
Okay. Ciao. Bye-bye.
Ευχαριστούμε πολύ, Μιχάλη. Γιάννης Τόλης.